We have Marcelo Atallah, who will tell us about fixed points of small Hamiltonian diffeomorphisms and the flux conjectures.
Oh, thank you very much for the invitation. I'm very happy to be here giving a talk. This is such a beautiful place. So today I'd like to tell a story about how two big conjectures in the field relate to each other in what was at least a surprising way for me. So these are the flux conjectures and Arnol'd conjecture. And this is based on joint work in progress with Egor Shelukhin. So first, let's just go over some basic definitions that we probably all know, just to set notation. Throughout this talk, M omega will be a closed symplectic manifold. And we're going to be mainly focused on Hamiltonian diffeomorphisms and the identity component of the group of symplectic diffeomorphisms. So what's a Hamiltonian diffeomorphism? Well, if you have a time-dependent function on your closed symplectic manifold, then you, by Hamilton's equation, you induce a time-dependent vector field, Hamiltonian vector field, and Hamiltonian diffeomorphisms are diffeomorphisms which are given as time one map of the induced Hamiltonian isotopy. And well, just to make sure we're on the same page, we say that a Hamiltonian diffeomorphism is non-degenerate if its graph intersects the diagonal transversely in M cross M. Let's just go over Arnol'd conjectures. So I split here in two different cases. So first, the non-degenerate case. So the Arnol'd conjecture in that case states that the number of fixed points of a non-degenerate Hamiltonian diffeomorphism is bounded below by the Morse number of your manifold, the minimal number of critical points in a Morse function. By Morse theory, that would imply that the number of fixed points is bounded below by the total Betty number. And after a lot of work, of which I'll include all the citations in the end, because I want to get towards the end by people in this very room, we nowadays know this. We know the number of fixed point is bounded below the total Betty number for any closed symplectic manifold. Now, this inequality, this is open in several cases. I think state of the art, it's known for the symplectic tori, CPN, and aspherical symplectic manifolds, if I'm not mistaken. I'm not sure if there's more cases where we know the Morse inequality. Now, in the general case, so including degenerate Hamiltonian diffeomorphisms, the Arnol'd conjecture states that the number of fixed points is bounded below by the critical number of manifold, the minimal number of critical points that a smooth function can have. And in particular, by the Sternlich-Schnellmann theory, that will imply that that the number of fixed points is bounded below by the cup length plus 1, where the cup length is just the maximal length of cup products that you can have of cohomology classes of positive degree. Now, because we're in the closed setting, the cup length is at least n, because wedging the symplectic form n times with itself gives you this, the volume form.
Let me make a remark. So Andreas Fleur thought that conjecture is wrong in general.
Yes.
But he thought it was too difficult to find a counterexample, and one should talk Dusa McDuff into it. That part never worked out. So.
Yeah. So
he thought that was the only person who could really do it reasonably.
Yeah. So part of the proof today, there's this analog of the flux group, the C0 flux group, and under the assumption that it has an accumulation point, we construct the Hamiltonian diffeomorphism, which is C0 small and has at most one fixed point. But now we can exclude. But it's ephemeral in the sense that if it's C0 small enough, we can exclude that from happening. But it does maybe give you a way of producing a counterexample in that sense. So yeah, thank you for the comment. So the cup length inequality, it's only proven in the aspherical case and for tori and CPN, but as Helmut mentioned, even Fleur believes it's not true in general. Okay, so now let's go towards the flux conjectures. Now we have these sequence of subgroups of the group of diffeomorphisms of a closed symplectic manifold. So this is the group of Hamiltonian diffeomorphisms, which is a subgroup of the path-connected component of the identity of the group of symplectic diffeomorphisms. Symp just denotes the diffeomorphisms which are symplectic, right, that preserve the symplectic form. And we're going to focus on two topologies, C0 and the C1 topology. And the C0 topology, one can think of it, well, as a topology induced by the C0 distance, which is defined by this formula here, where D is just some distance induced by a choice of Riemannian metric. Because we're in the closed setting, everything will be equivalent. And it's reasonable to ask whether each of these groups or subgroups is closed in either of these topologies in the subsequent group. So in this first case here, so looking at Symp inside diff, well, the symplectic condition is a condition on the derivative, so it follows pretty easily that in the C1 case, Symp is closed in diff. Now the C0 case, it's also true, but that's a lot harder to show, and that's the content of the Gromov-Eliashberg theorem. Now, the second inclusion here, so looking at the path-connected component of the identity, well, if we knew that Symp is locally path-connected in either of these topologies, then, well, it's a connected component, so it's closed. So it's a matter, if you can show that in particular, it would imply that it's closed. So the C1 case, that is true. And the reason why this follows is because if you have a C1 small symplectic diffeomorphism, then you can look at its graph inside a Weinstein neighborhood of the diagonal. And this graph, because we have control on the derivatives, this is going to be identified with the graph of a closed one form. And now you can contract that one form towards the zero form, and that will correspond to a symplectic path, a C1 small symplectic path, basically, from the identity to your C1 small symplectic diffeomorphism. So Symp is locally path connected in the C1 topology, and Sym0 is closed in Symp. And the C0 case, pretty much nothing is known. We don't know if it's closed in Symp. Probably for surfaces, it's not hard to show, but beyond that, we don't know. At least as far as I understand.
But you don't know a reference in the surface case?
No. But I thought a little bit about it. I don't think it's hard to. It probably follows from some. It will probably be corollaries of other theorems that are out there. But beyond that, I have no idea. But it would be interesting to see. And the flux conjectures relate to this first inclusion here, or this third inclusion, as I labeled. And we're asking whether Ham is closed inside Sym0. And in the C1 case, that's not a conjecture, that's a theorem. And it was proven in general by Ono in 2006. General meaning closed symplectic manifolds, with plenty of previous progress by Lalonde, McDuff, and Polterovich in '97. And in the C0 case, a lot less is known. It's pretty much open. And there has been progress by Hermann, proved it for symplectic tori, and some progress by Lalonde, McDuff, Polterovich in the same paper. And the state of the art is by Buchowski in 2013. And I'll go over some definitions before I can tell you what the progress was in the C0 case. So we want to ask.
It was Hermann, there was a consequence of Condit-Sinders theorem, or not?
I'm not sure. I'm not sure, but maybe. It's
because there was no Gromov.
Yeah, it's from '83.
Before nobody knew what to do, so it must have.
It must. I'm assuming it is, but I'm not quite sure. Yeah. Certainly, the type of progress from Lalonde, Polterovich, and Buchowski is very different. than what Arnol'd did. But they somehow don't use holomorphic curves. So I think that's interesting as well. So now let's go to the definition of the flux homomorphism. But before I'll define it a little bit more generally on what I call here map zero, which is on the universal cover map zero, which is the space of smooth maps from M to itself, which are smoothly homotopic to the identity. So not necessarily diffeomorphisms, just smooth. So the flux map is a map from the universal cover of map zero to the first theorem cohomology of the symplectic manifold in this case. So how do we define it? Well, classes here are just are represented by paths of smooth maps from M to itself, which are based on the identity. And we want to be able to evaluate one cycles. So what we do, well, we take some one cycle, we flow it by this path representing a class and compute its symplectic area. One can show that that is well defined, and moreover, it sends compositions to some. But this is not a group, so this is not a homomorphism yet. But when you restrict to the universal cover of Sim zero, then this is a homomorphism. This is the usual flux homomorphism that we know. So this allows us to define the topological flux group, which are the fluxes of loops of smooth maps. These are, in other words, this is the image of the fundamental group of map zero, seen as a subspace of its fundamental, universal covering under the flux map. And it's a subgroup of the first theorem cohomology group. And I think I'm gonna write down the definition so that when I mention it again later, you can keep it in mind. I'll leave it here. Maybe one. Can everyone see? Maybe share. If at some point you need me to, but these are just fluxes of loops of smooth maps. We're going to then compare that to the usual flux group, which is fluxes of loops of symplectic diffeomorphisms. So it's a lot more rigid. So let's now define the usual flux group and the C0 flux group. By work of Banyaga, once you restrict the flux group to the universal cover of Sim0, a symplectic path based on identity has zero flux if and only if it's homotopic relative endpoints to a Hamiltonian path. So in particular, if you have a symplectic path with zero flux, the endpoint is a Hamiltonian diffeomorphism. Now we have this, again, this sequence of inclusions where I still haven't defined this, but Ham0 just denotes the C0 closure of Ham inside Sim0. And of course, it includes inside Sim0. And if pi is the canonical projection of the universal covering of Sim0, now we can look at the inverse image of Ham0 under pi. So what are these? So these are classes in Sim0 that can be represented by symplectic paths based at identity and whose endpoint lie in Ham0. So in the C0 closure of Ham. And similarly, the pre-image of Ham, but these endpoints are just Hamiltonian. So the flux group, well, these are again fluxes of loops of symplectic diffeomorphisms. And equivalently, it's given by the image of this guy, so the pre-image under pi of Ham, under the flux map. So why do we have this equivalence? Well, if you have a class in the pre-image of Ham, then it's represented by a symplectic path whose endpoint is Hamiltonian. Then you can just find the Hamiltonian path connecting to it, and either by concatenating or composing with its inverse, you have a symplectic loop. But because this part of the path, which is dotted, is Hamiltonian, it has zero flux. So then the flux of your symplectic path just corresponds with the flux of a loop of symplectic diffeomorphisms. So that's how you get this equivalence here. And the reason why I wanted this equivalent definition is because now it becomes a lot easier to define the C0 flux group, which is the same thing, but now we're looking at the preimage of Ham0 instead of Ham. So now, for the topological flux group and for the usual flux group, we have this very nice description of fluxes of loops, either loops of smooth paths or loops of symplectic diffeomorphisms. For gamma 0, the C0 flux group, we don't have such a nice description, but we can characterize them as what we call almost loops. So what do I mean here? I mean that any class in the C0 flux group can be seen as the flux of a symplectic path whose endpoint is arbitrarily close to the identity in the C0 topology. So it's not, we don't get loops, but we get almost loops. And these will be very helpful later on, this characterization. So now, what's the relationship between the flux conjectures and the flux groups? Well, in the C1 case, so asking if Ham is C1 closed in Sim0, that's equivalent to showing that the flux group is a discrete subgroup of the first theorem homology. And that's in fact what Ono showed in 2006. Now, the C0 case, so asking if Ham is C0 closed in Sim0, that's equivalent to showing that the C0 flux group is equal to the usual flux group. And in particular, that implies that the C0 flux group is a discrete subgroup of the first theorem homology. However, we don't necessarily get this equivalence that we do in the C1 case. Maybe someone can find a way to get this equivalence, but so far we don't know how to. And the reason is that in the C1 case, we have this correspondence, right? For C1 small symplectic diffeomorphisms, as I alluded to in the beginning, their graph in a Weinstein neighborhood will correspond to a closed one form. But if you're C0 small, you're still going to be in some Weinstein neighborhood, but you're not necessarily graphical. So for that reason, we can't establish an equivalence here. So discreteness here would provide strong indication for the C0 flux conjecture. So what did Buchowski show in 13 and along with the Polterovich before him? Well, they show that if the topological flux group is equal to the usual flux group, then the C0 flux conjectures is true, it holds. Then Ham is equal to Ham0. And well, along with the Polterovich showed was exactly the same thing, but with the additional assumption that the symplectic manifold was a Lefschetz type. Now, showing that the topological flux group is equal to the usual flux group, it's quite hard to do. So basically, as tangible corollaries from this theorem in 2013, you know that aspherical symplectic manifolds with non-trivial Euler characteristic, you know that for them the C0 flux conjecture holds, but it's hard to come up with more examples that you know the gamma is equal to gamma top. And there are examples where these two groups are not equal. So for some symplectic mapping tori, for example. So now let me tell you a little bit about the relationship between the Arnol'd conjecture and the flux conjecture. So first, and it's going to be demonstrated in the proof of our first theorem, which is that the C0 flux group is in fact discrete for general closed symplectic manifolds. So this is some sort of weak version of the flux conjecture in some sense, but it does not prove it. In particular, because gamma is included into gamma 0, this provides another proof of the C1 flux conjecture. So how do we prove it? Well, we show that if we can guarantee that every sufficiently C0 small Hamiltonian diffeomorphism has at least two fixed points, then gamma is discrete. In other words, like I said in the beginning, under the assumption that gamma 0 has an accumulation point, we can construct a Hamiltonian diffeomorphism with at most one fixed point, which is C0 small. And the second theorem is that if phi is sufficiently C0 small, so phi being a Hamiltonian diffeomorphism, then it has at least cup length plus one fixed points. So in particular, because n is at least one, it has at least two fixed points. So from Gromov's work, you knew the existence of at least one fixed point, but two, we didn't know. Because this can, and in particular, the example that we construct is very degenerate in some sense. So we really needed to be able to show this lower bound, this coupling test. So this was known for a small Hofer norm by Schwartz. But this theorem follows from a more general theorem. So here's the thing. Fix some Weinstein neighborhood of the diagonal in M cross M. Now for sufficiently C0 small Hamiltonian diffeomorphisms, its graph is going to lie in that Weinstein neighborhood. So in particular, it's going to correspond to some Lagrangian submanifold of a codisk bundle. Now you can ask, well, is this Lagrangian exact? Of course, if the whole path lies inside of the Weinstein neighborhood, then it's going to clearly be exact because, well, Hamiltonian diffeomorphisms have zero flux and everything is going to follow from that. But if we don't know that, if perhaps the path strays far from the Weinstein neighborhood and then the endpoint comes back in, then what we show is that if it comes back in and it's sufficiently close to the diagonal or to the zero section, then it must be an exact Lagrangian. So now the question about fixed points of C0 small Hamiltonian diffeomorphisms becomes a question about intersection points of exact Lagrangians with the zero section. Exact, not necessarily Hamiltonian isotopic, but still the same tools apply, the algebraic tools. So what I mean is that the number of fixed points, well, it's going to be equal to the intersections of the Lagrangian graph in the diagonal. And that, as I said, the theorem implies that this graph is an exact Lagrangian. So now we can use some Lusternik-Schnillmann type arguments for spectral invariance of exact Lagrangians and obtain the cup length estimate for C0 small Hamiltonians. So now theorem B plus proposition 1 yield theorem A, right? Because we showed that what we can construct doesn't exist, at least for sufficiently small, if it's sufficiently small. Okay.
Is there, presumably not, but is there an example known of say in a cotangent bundle of sequence of Lagrangians going to zero, but in order to homotop them to zero, you have to go out? I mean, far out.
Yeah, because that would be a counterexample to the nearby Lagrangian vector. Well, at least a graphical version of it.
In a symplectic manifold, a Lagrangian where, yeah, it's presumably the same. I mean, you have a Lagrangian near a given Lagrangian, but zero. But in order to, you know, it isotopic to it, but where you actually have to go rather far out to invite certain things.
Yeah, you mean
I think it's nothing. Huh?
I don't know. Yeah, that would be quite.
It's,
That would be a source of several counterexamples. And just a remark, if we knew that the symplectic manifold were rational, so the symplectic areas of spheres formed a discrete subgroup of the reals, then theorem C, which is the theorem about exactness of the graph, would follow from easier arguments which are already implicit in the work of Lalonde, Todorovic, and the work of Buchowski, basically showing that the norm of the Louisville form is somehow controlled by the C0 distance. But the epsilon that you get in those cases, it tends to zero as the rationality constant goes to zero, so rational approximation doesn't work there.
Yeah, so in the context of this Lusternik-Schneermann version, I think what Fleur was thinking of, taking products of symplectic manifolds, which would destroy rationality and so on.
Right, so that that would make sense. So you make sense. Yeah, I'll go over the construction and maybe there's it's somehow, if you can avoid this theorem, there's a way of constructing this counterexample, but it's hard to make sure that you're not within the frame, like you're not far within a Weisser neighborhood, then you see what I mean in the construction. I'll try to get back. So let's go to the content of proposition 1, right? Now I'm going to spend most of the time just constructing this counterexample under the assumption there's an accumulation point in gamma 0. So there's this great theorem by Farber and Schutz from 2006, and it's a theorem about one forms. What it says is that if you have a non-trivial first cohomology class, then you can find a representative which has at most 1, 0. It's a closed one form with a most 1, 0, which represents that class. Of course, this one form has to be, the class has to be non-trivial, otherwise you would contradict the Lusternik-Schneermann theory here. And what we first do is quantify this theorem in some sense, because what we want to do is be able to use this one form to induce a symplectic isotopy. So in the same way that you have a Hamiltonian isotopy induced by a vector field satisfying Hamilton's equation, you can, instead of having an exact one form here, you can just have a closed one form, and that will induce a symplectic path whose flux is precisely the cohomology class of that one form. So now we have control over the zeros of this one form, but we want control over the fixed points of the symplectic isotopy, of its time one map. And the way to do that is being able to control its C1 norm, because then you avoid these new one periodic orbits forming. So you just want a correspondence between the zeros and the fixed points. So this is the point of this first lemma here. It's a lemma only about closed one forms. So what we show is that not only, I mean, H upper 1 is just some real vector space, so we can fix some norm on it. And what we show is that there exists a C such that we can pick this representative from the Farber-Schutz theorem, but that its C1 norm is going to be controlled by the norm of the class with this uniform C. Does that make sense? Okay, so how do we prove this lemma? So first we pick some non-trivial class, homology class, and pick the representative given by the Farber-Schutz construction. So that's going to have at most 1, 0, and we can suppose, which is a bit, we can take care of the case where it has 1, 0, which is a bit harder. So this graph is going to look something like this in the cotangent bundle. So you have only 1, 0, and we can pick some contractible neighborhood of the 0 in the base, in the manifold. Now, away from this from the fibers of this contractible neighborhood, it's going to be at some delta distance away from the zero section for some choice of metric. That's not whatever you fix, there's going to be some positive delta away from this contractible neighborhood. Now you can find a small enough neighborhood of the origin with the norm that we fixed in H upper 1, for which every cohomology class or non-trivial cohomology class can be represented by a one form whose C1 norm is small compared to this delta here. So their graphs are going to be something like this, right? Just by picking a small enough neighborhood of the origin. Now, by Poincaré's lemma and a little bit of work, we can show that not only we can pick the representative with small C1 norm, but we can pick it to vanish identically on the contractible neighborhood. So now when we add this represented, so alpha plus beta, so alpha was the special one form that we took from the Farber-Schutz construction. We're not changing the zeros inside this neighborhood because we're just adding 0. But because it's small away from the neighborhood, we're not creating any new zeros away from it. So alpha plus beta is going to have the same 0 set, and its C1 norm is only going to depend on the C1 norm of alpha and plus delta over 2, which is the delta that basically only depends on alpha, and alpha is fixed here. So we can call the C1 norm plus delta over 2 just some CA here. But note that an epsilon neighborhood of the class A is just A plus epsilon neighborhood of the origin. So every cohomology class here can be written as alpha plus beta in that same way. And we can do it in a way that by the same argument, we can do it in a way where the 0 set is the same and the C1 norm is bounded by CA. So suppose, for example, that we started off with an A that had norm 1, then it's sitting on some sphere, and we prove the lemma basically for some constant for a ball around that point. Now we just conclude by compactness because we can extract the finite cover and we maximize over this. So what did we show? Just coming back, we show that we can find, given some norm here on H upper 1, there is a constant which allows us to control the C1 norm of this special representative by the norm of the cohomology class. But this is a theorem only about closed one forms, so now let's translate it to the symplectic world and to get what we want. And basically we have this corollary, which states that for for any epsilon, we can find a sufficiently small neighborhood of the origin in the first around cohomology group, for which every non-trivial class, well, not only it will have this special representative with a most 1, 0, but the symplectic isotopy that it induces via this equation here is going to have its time one map, the fixed points of the time one map is going to correspond to the zeros of the one form. So it's going to have at most one fixed point. And the flux of that path is going to be precisely that cohomology class. And moreover, it's going to be C0 small. Because and all you need to know is that the C0 distance here is also controlled by the C1 norm in particular of the one form. So that's just basically, there's nothing, this is just translating the work from the lemma to a corollary that's going to be helpful for us. Okay, so now let's use this to prove a model version of what we want to show. So let's do the C1 case and use that construction. So what I mean is, using that corollary, we can show that there is an equivalence between the stronger Arnol'd conjecture for C1 small Hamiltonian diffeomorphisms and the C1 flux conjecture. I mean, of course, now we know the C1 flux conjecture holds, and the strong Arnol'd conjecture for C1 small, I haven't seen it written before, but it could have been deduced since the work of Arnold in 2006. So C1 small, I mean just the endpoint. For the whole path, it's not hard. But let's use this construction to prove the theorem, this proposition. So let's first look at this direction. So here we're going to do what we want to do in the C0 case, but in this easier setting. We want to show that if there's an accumulation point in the usual flux group, then there's a C1 small Hamiltonian diffeomorphism with at most one fixed point. But note that here it's very helpful that we have a loop. Maybe you'll see when I do this argument. So we can pick U epsilon, which is that for some arbitrarily small epsilon, take U epsilon, which is the neighborhood that we constructed in the corollary, for which we can produce that symplectic isotopy with flux equal to that cohomology class and with the most one fixed point. So take A in this non-trivial and in U epsilon and in the flux group. But because it is in the flux group, it's represented by some loop. Now, take the special representative. So A is a cohomology class in a very small neighborhood. So we can take that special representative that we've been constructing. In particular, the induced symplectic isotopy will have at most one fixed point, and its flux is going to be equal to A. So instead of taking that exact representative, we just take minus of it, so that the flux is minus A. And now we compose the loop with this symplectic isotopy that we've been constructing. By construction, this is going to have zero flux because the flux homomorphism is, well, it's a homomorphism. The flux of the loop is A, and the flux of this induced isotopy is minus A. So the time one map of psi t here is a Hamiltonian diffeomorphism. Now, the time one map of psi t is also the time one map of psi minus alpha, because psi t here is a loop. So in particular, its fixed points are going to correspond to the fixed point of psi minus alpha. So it's going to have at most one fixed point. So it's a Hamiltonian diffeomorphism with at most one fixed point, and you can make it C1 small just by taking this A as small as we like. Now, on the other direction, if you have a C1 small Hamiltonian diffeomorphism, then, like I said, its graph is going to lie in the Weinstein neighborhood of M cross M, and it's going to be identified with a closed one form. But a priori, we don't know that that form is exact. So what we can do is use that deformation, right, that I was explaining in the beginning, use the fact that simp 0 or simp is C1 locally path connected, and connect it to the 0 section, which would, what we're really doing is taking the C1 small Hamiltonian diffeomorphism and making it into a loop. And the flux that we get is precisely the class of this one form. But it's a Hamiltonian path, so we have no flux going all the way to the endpoint. And then by completing the loop, we just get the flux from the one form. So, but if this Hamiltonian is C1, it's arbitrarily C1 small. So we can, which means that the cohomology class of this one form is small as well. But since we know we're assuming that gamma is not discrete, that's not possible. So if it's small enough, it has to be 0. So then that one form is exact, and everything follows from Moore's theory and Lusternik-Schulman theory. So the construction helped us in this direction here. And that's what we want to do in the C0 case now. But now we don't have loops. So that's the tricky part. This idea of just composing and knowing that the time one map is the same, that's not going to work, at least not without working a bit harder. So let me recall what we want to show. Well, we want to show that if gamma 0 has an accumulation point, then we construct the C0 small Hamiltonian diffeomorphism with a most one fixed point. So again, we take this U epsilon, which is that neighborhood where all the this is a neighborhood in the first around cohomology, and all the cohomology classes can be represented by these one forms that induce these symplectic isotopies with at most one fixed point. Now we take A, which is both in U epsilon and gamma 0. Now take the isotopy that corresponding to minus alpha, minus the representative. So its flux is going to be minus A, it's going to have a most one fixed point, and it's going to be C0 small. So this is all from that corollary that came straight from the lemma that we proved. And what we want to do? Well, now we want to use this description because we know that A is in gamma 0. So in the beginning, I said that cohomology classes in gamma 0 can be represented by these almost loops. If it were a loop, we would just compose and we would just follow the same argument as before. But it's not. It's C0 close, so we need to work a little bit hard. So let's first suppose, so here, we know that there's either one or none fixed points. So let's first suppose that there are none, which is a little bit easier to deal with. So suppose that there are no fixed points. And so maybe what I want to do, let me see if what happens is the following. So suppose you have no fixed points. Now your graph is going to be far from the diagonal, right? So let the blue line be the graph of this the time one map of this isotopy that we're inducing. So it's going to be far. It's going to be some positive. So it's just before I go over what we would like to do is something similar that we did in the lemma for the one forms. But now we're not talking about adding one forms. We're talking about composing maps. But still, there is some sort of control if we're composing with something that's small enough. So in the case where there are no fixed points, well, the graph is going to lie at some positive distance from the diagonal. And now we take this almost loop arbitrarily close to the diagonal. We can get as C0 close as we want to the diagonal. And in particular, and then we compose these two things. So we define psi t here by composing that isotopy with this almost loop. So the time one map, you can check that the distance between x and phi x, where phi is the composition, is bounded below by this difference here. It's not a hard calculation. And it intuitively makes sense. So if you're far from having a fixed point and you're composing with something very small, you're not going to create any new fixed points. And moreover, by what I explained before, this is a Hamiltonian diffeomorphism because the fluxes are canceling out. So we're constructing it in precisely that way. And it's going to be C0 small because this epsilon that we're taking is arbitrary in the beginning. So the idea is we fix this graph here for any epsilon, and then we choose the almost loop small compared to that epsilon. But this means that we have control over its C0 size because it's composing two C0 small symplectic paths. Is that okay? So in this case, we built a Hamiltonian diffeomorphism, which is C0 small and has no fixed points because we're assuming there is an accumulation point and that the representative has no zeros. Okay, so now what if it has one fixed point? That's a bit harder, right? Because so if it has one fixed point, it's going to be something like this blue line that I drew. So a graph, so very similar to that one form picture. But no matter how C0 close I take the endpoint of that almost loop, when we compose, you can create a bunch of new fixed points here. So you lose all of that control. So when we were dealing with one forms, we could use Poincara's lemma and make it vanish around a contractible neighborhood. And now we don't have Poincara's lemma, but what we do is this quite fantastic trick of Buchowski, Humilier, and Sefadini. So they use this to prove the C0 continuity of the spectral norm for a spherical symplectic manifold, so that by passing to n cross n, you can assume that your symplectic path is supported away from a small ball. And the way you do it is you start off with some symplectic path. So suppose that this is the endpoint of that loop, of the almost loop. Then you look at psi cross psi minus 1. And locally, you take the symplectic diffeomorphisms that switches coordinates. And then you conjugate by that. And if you see what's going on is that locally you're not doing anything. And away, if you take it supported in a small ball, you're not changing psi cross psi minus 1 away from that small ball. Inside a smaller neighborhood, you're the identity. And maybe something's happening between these two balls. But what we really needed is that it's identity on the ball. And that whatever is happening between these two neighborhoods is not C0 big. And we can get control of that. So now once we have that, we can now compose. So we compose that isotopy with this almost loop, whose endpoint is supported away from a ball, and we just pick that ball to be where the fixed point is. And what happens is we don't create any fixed points in that neighborhood, and we still have C0 control over whatever happens outside of it. So we just take it C0 small enough that you don't create any fixed points away from the neighborhood. And again, everything follows in terms of the flux is going to cancel out by construction. So it's a Hamiltonian diffeomorphism, has one fixed point, and it's C0 small. And of course, this was under the assumption of an accumulation point. But this is excluded by the coupling estimate for C0 small, if we take epsilon arbitrarily small. So this proves a counterexample. What I did here is still possible, but you would have to find an example where whatever you construct does not fall within the epsilon of the theorem of the C0 small Arnold conjecture. But I haven't been able to do it so far, but it's a possibility. So in this case, it's ephemeral, right? We construct this thing and show that it can't exist. So let me, I have until 1:30. Okay. So I'll just, while we didn't show the C0 flux conjecture in general, we did prove it in a few new cases. So I just want to go over them. So if we suppose that the symplectic manifold is spherically monotone, so here we're asking for proportionality between the homology class of the symplectic form and the first-order class associated to a symplectic manifold on spheres, and we're allowing the proportionality constant to be 0 here, so a spherical in some sense. So if we're spherically monotone and you satisfy either of these conditions here, the C0 flux conjecture holds. So for example, if Euler characteristic is non-zero and you're spherically monotone, C0 flux conjecture holds. If fundamental group has finite center, then C0 flux conjecture holds. If moreover, this proportionality is over all of H2, not just spherical classes, then C0 flux conjecture holds without any further conditions. So for what the monotone case, basically what you usually call. And there is this slightly more technical condition here, which basically we just have it because we can find an example of a symplectic mapping tori which satisfies the third condition, but for which the topological flux group is different from the usual flux group. So it's basically showing that there is an example that wasn't covered by there's an example that's provably not covered by the previous work, but it's covered by this current theorem. And moreover, this is not written here, but it's a recent development. If the symplectic manifold is of Lefschetz type, so without any assumption of spherical monotonicity, then we can also show that the C0 flux conjecture holds in this case here. So if Euler characteristic is is non-zero, or if the fundamental group has finite center. And so, this Euler characteristic non-zero condition here, it appears a lot. And the reason why it's usually there is because, so if you consider the map from pi1 of sim0, the evaluation map, right? It takes a loop of symplectic diffeomorphisms, and you evaluate and you see what class. So you look at its orbit class in pi1 of the symplectic manifold, right? If it's Hamiltonian, then we know that that class is trivial. But when Euler characteristic is different from zero, then that evaluation map is always trivial. So that's somehow important in the background of what's going on here. So if Euler characteristic is zero, then that map is not trivial. So if you can you take rotation of T2, and that gives you non-contractible classes for a symplectic loop. And moreover, what we show is that in the spherically monotone setting, in either of these three situations here, the flux map, which descends into from sim0 to the quotient, is C0 continuous. And this is new even in the case of the torus, of symplectic torus. And the first time I came across this problem, I thought that maybe the strategy was proving that this map is C0 continuous to show that the C0 flux conjecture holds. But somehow it's harder this way. But the methods in this spherically monotone case actually yield the C0 continuity. And well, this is what I prepared for you today. So thank you very much for listening. And as I promised, here are the citations and references for the work on Arnold conjecture. Thank you very much.
I have a question. Can you explain where the conditions in theorem D come from? Like why?
Okay. So you want this, right? So
Yeah, but also the monotonicity. Why?
yeah,
Is it important?
it is important. So for the methods that we have so far, it's important. It's not just it helps with the technicalities, because in the end of the day, we want to compare ranks of Morse homology and Morse-Novikov homology. So to do that, we're using Floer-Novikov theory. And Floer-Novikov theory behaves well in the spherically monotone setting, in the sense that Floer-Novikov homology. So Floer-Novikov homology is analogous to Floer homology, but for a non-exact symplectic path. And in the spherically monotone setting, it's isomorphic to at least the ranks are equal to the Morse-Novikov rank. Now, if you are at least with the variant of Floer-Novikov theory that we use, if you're not in the spherically monotone setting, then that is not true in general. So, for example, whenever we're in these settings where Floer-Novikov is isomorphic to Morse-Novikov, you know, for example, that the evaluation map is injective in some sense. So if you have a loop of symplectic diffeomorphisms whose orbit class is trivial, then that loop has to have zero flux in these cases. But there are examples, so by McDuff, by Tolman and Zhang, of symplectic circle actions which are non-Hamiltonian and have fixed points. So that tells us that in these cases, that variant of Floer-Novikov homology cannot be isomorphic to Novikov homology. So there are things, of course, in some parts, monotonicity is helpful, just technically speaking, but there are non-trivial parts where it's important in this case. Thank you for the question.
I have another question.
Sure.
You said that maybe these arguments can help construct a counterexample.
Yeah.
And there was this relation to the, well, at least the C1 small version of, you know. So there's like the C0 counterexample for the Arnold conjecture. Is it like, do you think it could be relevant, or is it like totally disconnected?
It's relevant in the sense of whatever, if you want to understand if the tools that you're using, if they're C0 analogs, are stable in some sense. So if you know that there is a counterexample, then it's easy to see that certain things are not going to hold. So
yeah, but you cannot use it to construct.
So far, yeah, but it's certainly a way to look at it. Maybe there's something there. Yeah, like
I think they tried
to make it
that to find sort of a smooth counterexample.
Yeah, no, it's a very crazy example.
Because it's just not smooth at one point, right? That's
that's exactly
which is exactly the here. The idea here is more take this closed form with MOS10 and see if you can combine that with a case where you know that while the flux group is not non-discrete, maybe the flux is small enough that you can find a small enough loop and not create any new orbits, and then that would also do it.
So you believe the flux conjecture is correct?
I mean, because on the one hand, there are non-trivial problems to generalizing this proof. So going beyond that. Beyond that, and
but is that problems of machinery or lacking machinery or viewpoint or presumably viewpoint?
So it's this machinery, the way it's set up right now, the way we do it, won't yield the full without additional ideas.
But you have dreams about machinery which perhaps exists.
Yes,
but has to be developed.
I'm more inclined to believe that it is true. And if it were, I feel it's also certainly connected to nearby Lagrangian conjecture in some sense, right?
Yeah.
Some specific case. So a counterexample, not that tells you that it should be true, but
what is the general belief about the nearby Lagrangian conjecture of today?
I don't know. I mean, what's interesting is in theorem B, I think, you have the exactness of that graph. But even if you knew nearby Lagrangian conjecture, that would allow you to find a Hamiltonian isotopy, but of M cross M to bring it to close the loop. So even knowing the Lagrangian nearby conjecture wouldn't immediately give us what we want, because we would need this isotopy to be graphical in some sense. We would need a Hamiltonian isotopy on M, not M cross M. But now at least we know that it's exact. That the graph of the Hamiltonian diffeomorphism. Yeah.
Okay, if there are no more questions, let's thank Marcelo again.